Hi all, my name is Preetham Bharadwaj. I am studying in first year, first semester in BTech in SRIT College. Today the topic we are going to discuss about is body-centered cubic structure. Body-centered cubic structure. It is a subtopic which comes under crystal structure in solid state physics. Introduction to crystal structures. Crystalline solids are characterized by repeating ordered management of atoms. That is, the crystals are formed by the arrangement of atoms repeatedly in an ordered manner. So the three common cubic crystal structures we see are simple cubic structure, body-centered cubic structure, face-centered cubic structure. Today we are going to talk about body-centered cubic structure in detail. Definition of BCC structure. The body-centered cubic structure is a type of cubic crystal arrangement where the unit cell is shaped like a cube with atoms positioned at each of the 8 corners, and a single atom is located at the center of the cube. This results in a total of 2 atoms per unit cell. One atom from the center and a contribution of one atom from the 8 corner atoms. Hence its coordination number capital N is 8. So the in a BCC structure, the one atom is at the center of the crystal and it is surrounded by 8 corner atoms. So this results in the formation of 2 atoms per unit cell. The unit cell is in the shape of a cube, whereas the atom is in the shape of a sphere, as we know. The effective number of atoms per unit cell is 1 by 8 into 8 plus 1, which is 2 atoms. So we have discussed that in one unit cell there are 2 atoms. Next, the derivation of atomic packing factor. Atomic packing factor is defined as the ratio of total volume of atoms in the unit cell to the volume of the unit cell. So the atomic radius small r can be derived from the given figure as from triangle ADB by applying Pythagoras theorem. AD square equals to AB square plus BD square. AD square equals to A square plus A square. AD square equals to 2A square. Next, from triangle AHD, again by applying Pythagoras theorem, AH square equals to AD square plus DH square. So 4R square equals to 2A square plus A square. 4R square equals to 16R square and 2A square plus A square equals to 3A square. From this, R square equals to 3A square by 16. R equal to root of 3A square by 16. So the atomic radius small r is root 3 into A by 4. Next, the lattice constant A, which can be derived from the atomic radius, is A equal to 4R by root 3. Nearest neighbor distance 2R equals to root 3 into A by 2. Now, the volume of all atoms in the unit cell nu equals to 2 into 4 by 3 pi r cube. In one unit cell there are 2 atoms and the volume of the atom, which is shaped like a sphere, is 4 by 3 pi r cube. Hence nu equals to 2 into 4 by 3 pi r cube. Volume of the unit cell V equals to A cube. Since the unit cell is in the shape of a cube, its volume is A cube. Now APF equals to nu by V. APF equals to 2 into 4 by 3 pi r cube divided by A cube. Now APF equals to 8 by 3 pi r cube whole divided by 4r by root 3 whole cube. Now which is the lattice constant. Now APF equals to 8 by 3 pi r cube whole divided by 64 r cube by 3 root 3. Now APF equals to, by solving the equation, we get pi root 3 into 8, which is 0.68. So APF is equals to 68%. Therefore the atomic packing factor of a BCC structure is 68%. Conclusion. After finding the atomic packing factor for BCC structure, we can conclude that it has a APF of 68%. That means 68% of the unit cell volume is occupied by atoms, while the remaining 32% is an empty space, or we can call it as a void. BCC has lower packing efficiency compared to FCC structure, which achieves 74% packing efficiency. Now by applying the same method for FCC structure, we can get the APF as 74%, which is higher than the BC structure and SC structure. Examples. Common examples of materials with a body-centered cubic structure is iron, chromium, tungsten, molybdenum, vanadium. These materials are in the shape of crystal which has body-centered cubic structure. Thank you.